In order to decide if a function is continuous or not, what we need to decide on is what's the definition of continuous. An easiest definition that we can come up with right now is that it can be drawn in one pencil stroke. The function that we have graphed over here to the right, we can see that this is not a continuous function. In fact, we can see that it has three different parts. We would have to pick up our pencil. We'll draw one leg, and then we'll draw the middle one, and then we pick up our pencil again to draw the last one. So this is not a continuous function. Let's go to our parent functions and determine which of those are continuous. You may want to pause the video here so that you can test yourself and see if you know the definition of continuous functions. We find that the constant function is continuous. So I'm going to write down continuous like this in terms of an abbreviation. Linear functions are continuous. Absolute value is continuous. Square root is continuous. Cubic is continuous. Cube root is continuous. Reciprocal is not continuous, so I'm not going to write down that it is. Reciprocal is not continuous. The logarithmic is continuous. Exponential is continuous. And the sine wave is also continuous. One of the things that I want you to notice is that when we're looking at continuous functions, notice that their domains are in one pieces. It may not be from negative infinity to positive infinity, but it is not broken up into pieces, and this is what I mean by that. If we look at reciprocal and reciprocal squared, we can see that our domains are broken up into pieces, in fact two pieces, one for each branch of our graph. And so that's the reason why these two functions are not continuous. Let's talk about even and odd functions. Even and odd functions, or that description, is actually about their symmetry. In fact, what we find are that even functions are symmetrical about the y-axis. And we find that odd functions are symmetrical about the origin. One easy way to kind of remember which is which, if you put your pinkies on the y-axis and put your hands up and down, open them like a butterfly, think of it as opening it like a book. If you can do that, that means that what you see on the left side is the exact same thing you see on the right side. And what we're going to do is go through our parent functions and determine which one are even and which one are odd. But the easiest way to think about it is that it is even if you can see what you have on the left side is the same thing as you see on the right side. If you were to fold it along the y-axis, they would line up, what you have on the left and what you have on the right. For odd functions, think of it as upside down. If I were to put my graph upside down, would it look the same? If it does, then it is symmetrical about the origin. So let's take a look at our parent functions and determine which ones are even and which ones are odd. Now, the graph can also be neither. We're going to see an example of that as well. So let's test the even. If we put our fingers right here on the y-axis, the question is, what we see on the left is the exact same thing we see on the right. In our case, it is. So we're going to write down that the constant function is even. And we're going to do the same thing with my linear function. In other words, what I see on the right is the same thing that I see on the left, and we see that it's not. But now the question is, if I were to spin my graph upside down, would it look exactly the same? And the answer is yes, so this function is actually odd. Let's take a look at absolute value in quadratic. If you imagine a mirror right here in the middle on the y-axis, what we see on the left is the exact same thing we see on the right. It is even. And we could see that the same thing is happening with the quadratic. This is even. If we look at the square root, if I sit here and look at my y-axis, what I see on the left is the exact same thing I see on the right. In this case, it's not true. However, if I were to put this upside down, it would probably look like this, which is not the same thing as what we have up here. So therefore, this is neither even nor odd. Now, I'm not going to write anything, but you could write neither if you like to realize that this is neither even nor odd. If we look at cubic, I don't see the same thing on the left side as I do on the right side, but if I were to put this upside down, it would be the exact same graph. So this is an odd function. Cube root has the same scenario. If I put it upside down, it will be the exact same graph. For reciprocal, if I put this one upside down, it would be the same graph. So this is also considered odd. If we look at a reciprocal squared, along the y-axis on the left compared to the right, we will find that this is even. Logarithmic, we're going to find that this is neither. And for exponential, we will find that it is neither as well, meaning that we cannot see the same thing on the left and the right, and if we put it upside down, it will not be the same graph. For sine, believe it or not, if I were to spin it around, it will be the exact same graph, so this one is also odd. Now, one of the things that you might see about even and odds are going to be those y values. We want to make sure the y values are the same on the left and on the right. One of the things I want to point out when we're talking about intervals here, remind yourself that intervals are going to be the x values. Those are going to be part of our domain. And the describing words that we have here, increasing, decreasing, or constant, those are describing the y values. So when I'm asking for an increasing interval, what I'm going to say is I'm going to write down increasing interval, and then I'm going to write down when is it increasing. For the graph that we have over here to the right, if I imagine myself marching from left to right, my y values are increasing, always getting bigger and bigger. So we can see that one increasing interval is from negative infinity until we get to the number 1. And I'm not going to include the value of 1 because actually it's undefined at that point. But what I want to remind you of is that the x's are going from here until we get to 1. The y values are getting bigger and bigger and bigger and bigger. So the increasing part describes the y values. My interval part describes the x values. And we can see what happens between 1 and 3. Well, starting at 1, a little bit larger than 1, we see our y value is here, and then it comes down and comes down and comes down and comes down and comes down. So we can say we have a decreasing interval from the point 1 to 3. And if we go to this last segment over here, starting at 3 until we get to infinity, our y values are also decreasing. So we're going to say that it's decreasing as well from 3 to infinity. Now this one does not have a constant interval meaning that the y values will stay the same and then the x values are changing. So let's go to our parent functions and determine increasing, decreasing, or constant intervals. So for our constant function, we will actually see that our y values remain constant. So we're going to write down that we have a constant interval, and that interval is from negative infinity to positive infinity. In other words, it's always a constant, or our slope is always 0 is another way of saying it. For linear, we can see that as we're starting over here on the left and marching to the right, our y values are actually getting bigger and bigger and bigger all the time. So we say that that is an increasing interval from negative to infinity to positive infinity. So remember that these values over here are going to be similar to our domain values because they're both describing x's. When we go to absolute value, if I start way over here at negative infinity, our y values are actually getting lower and lower and lower till we get to the 0, and then it's going up higher. So we have both a decreasing interval from negative infinity until we hit x is equal to 0, and an increasing interval from 0 until we go to positive infinity. Notice that when x is equal to 0, it's at this little vertex. We don't know if it's increasing or decreasing at that point. That's the reason why we leave it with an open parentheses at the 0 value. Quadratic is very similar to absolute value in that we have a decreasing interval and then we also have an increasing interval. So decreasing from negative infinity until we get to the x value of 0, and then increasing interval from 0 to infinity. For square root, we can see that our domain starts at 0, so we're not going to have anything over here at negative infinity. We're going to start here at 0, and notice that my y values are getting bigger, so it's always increasing from 0 to infinity. Again, I don't include the 0, but we do say it's increasing from a little bit larger than 0 all the way to infinity. Cubic, if we start at negative infinity over here, we see our y values are always getting bigger, so it is increasing from negative infinity to infinity. Cube root, slowly but surely our y values are getting bigger, so this is actually an increasing interval from negative infinity to infinity. For reciprocal, if we're going from negative infinity to 0, we see our y values are actually getting smaller, so it's decreasing from negative infinity to 0. And then on the other side of 0, we can see that it's also decreasing from 0 to infinity. We cannot put from negative infinity to infinity because we have to take into account that when x is equal to 0, we don't even have a value. So notice that our domain for our reciprocal function is very similar to what we're seeing over here for our decreasing intervals, then broken up into two parts. For our reciprocal squared, we can see that our y values are getting bigger, so it's increasing when we started at negative infinity until we got to 0. And then on the other side, we can see our y values coming down, so those are decreasing from 0 to infinity. Logarithmic, we can see we're going to have our intervals going to be from 0 to infinity. That's what our domain says. And we can see that those values are constantly increasing. So we're going to write down increasing from 0 to infinity. For exponential, our y values are also getting bigger. So we're going to say it's increasing from from negative infinity to positive infinity. For the sine wave, actually what happens here is we have it going up from here till we get to here, and then it's going down from here until we get to here. So we're gonna write that down just for right now, but it actually keeps repeating itself. And when we get to trig and we start talking about graphs, then we'll talk about how to write that down. But for right now, let's just take into consideration this part of our graph. So we say that it is increasing from negative 90 degrees until positive 90 degrees, and then it was decreasing from 90 to 270. So we'll write decreasing from 90 to 270.